Hey everybody, we're going to do a quick review here over this graphical analysis idea. So the first thing I'm going to start with is our position versus time graphs. And so we're going to make it look like this. And most of the time we have the position and time set up like this. And so remember, we called this like an XT graph in our lab, right? So once again, we are looking at position versus time. And over here, our position is going to be X, and we're going to call that in meters over here. And then our T is going to be in seconds over here. And so what happens on this is, what this is telling me is that it's exactly what the position is doing. So I have a couple of examples here I want to walk through real quick. This right here, this means that I've traveled some kind of constant velocity away from the origin. And it looks like right there, I'm just label it constant velo plus. And then I have another chunk that I'm going to look at. I'm going to go from here to here. And it looks like this part is now, he is at rest. The particle is now at rest of the object. So some major points to make sure we remember about this is that the slope of a position versus time graph is velocity. And the graph tells what the direction and the magnitude is. So the first white chunk looks like it has a positive slope, so it has a positive velocity. The one in red, right, is at rest, so its slope is 0. It doesn't have a velocity. And then finally here in blue, I'm going to sketch this idea here that it looks like it's going down. Once again, this is a constant velocity in the negative direction, right? So the graph told me what was happening here. And so on purpose, we talked about this being constant velocity. Well, if I have a position versus time graph that is curvy, we talked a lot about this, right? Here's my axes, M and S for meters and seconds. If I have a curvy up, right, this means my object is going in the positive direction and getting faster. So we talked a little bit about sketching the slopes at different points. So I'm going to have this right here, this guy right here, and this guy right here. So notice that slope is changing, right? My slope is changing. That means it's actually getting faster, right? So what this would be an example of is the velocity would be positive and the direction is positive, which means the acceleration would be positive, right? It's getting faster in the positive direction. If I have one that looks something like this, sloping down, right? Once again, if I were to sketch the slopes of the tangent line, it looks like my velocity is going in the negative direction. The direction is in the negative direction there. So it looks like it's speeding up in the negative direction. So we have to make sure we understand what that looks like. We have one more kind of idea here that we can look at it this way. If I have a curve that's doing this, my tangent lines start leveling off this way. The object here looks like it is slowing down. So here, the direction looks like it would be positive, yet the velocity, right? It looks like it's slowing down. It'd be negative, okay? So that means the acceleration would be negative because the object would be slowing down. And that's an important idea that we want to talk about there. All right, so there's position versus time. Let's take a look at what velocity versus time looks like with these ideas. A velocity versus time graph is just kind of like it says. Velocity, that's going to be in meters per second. And then a time, once again, is in seconds. And the slope is acceleration, and the graph tells the direction and magnitude. So here's an example of this, and the velocity versus time graphs can kind of be boring, but here we go. Here we have this piece right here, And what this is telling me is that this is a constant velocity in the positive direction. And we've talked a lot about this in class. We can't have hard edges on these graphs in real life, but once again, they're nice to see what's going on here. Here, this is a constant velo here, but it's actually 0, right? So this means it is at rest if it's at the 0 line right here. That's what that means right there. Jump down here, my dots. This line right here is a constant velocity, but this would be going into the negative direction, right? So what we have on this graph is that we have 3 phases of velocity. We have a positive velocity in the red, and it's not changing. We have a constant velocity of 0 at rest, then the blue, and then we have a constant negative velocity, negative 10 meters per second, for example, in the green. That's what that would stand for. Now, these are all constant velocity graphs, so let's do one that has an acceleration. The only time we are going to see curvy graphs in this class is going to be with position versus time, so make sure you remember that. But if something is accelerating in using a velocity versus time graph, we illustrate it using this way. So here's my first sketch right here. Here, my initial velocity was 0, and then my final velocity is some value, let's just call this 10 meters per second for fun. Notice the velocity values changed, so that means I had to accelerate. So here's an example, it's accelerating. Right here, it's at a constant velocity that is positive. And then for this last chunk here, it has a negative acceleration. And over here, I forgot to say positive acceleration. So this is an example of what it looks like when we have the an object is accelerating and going at a constant velocity and then accelerating again, only in negative direction, and then coming to rest again. One more thing about velocity versus time graphs is it tells us the displacement if we take the area of it. So here's my velocity versus time graph. So here's my my axes here. And so for this first thing I'm going to do is I'm going to just say, all right, my problem told me my object had some kind of constant velocity. Let's just say this is 10 meters per second. And it took 5 seconds for us to get there. So the easiest thing to do is we look at the area under the curve. And so we have this right here, that is 5 seconds here. The height is going to be 10 meters per second. So the area of a rectangle is pretty straightforward. Length times width. The length, let's call this 5 seconds. The width, 10 meters per second. We notice that the seconds cancel, leaving me with the meter unit. So we get an area of 50 meters, or the displacement of this particular object was 50 meters. Cool, cool. Well, what if an object is perhaps has a negative acceleration? So here's how we'd be able to handle this. Let's say it took another 5 seconds for the object to reach it here. And now I have this velocity over here. Let's call this negative 10 meters per second. That's what this value would be here. So once again, what I would do is I would take the area of this shape right here. And so the area of a triangle is 1/2 base times height. Well, the base of this guy is 5 seconds, right? From 10 to 5, so make sure we understand that part there. The height in this case is negative 10 meters per second, right? We're looking at the delta, so it gives me a negative 10. So if I crunch my numbers real quick, I get a value of negative 25 meters. And so Once again, this is telling me the displacement of the object. And this is really important, okay? The white area up at the top here is giving me the displacement for the first chunk, and the green thing is giving me the displacement for the part where he was accelerating in the negative direction, okay? So there's a couple of different answers we can get for asking a question like this, right? I can say, what is the total distance? And for the distances, we would simply add these two values to get 75 meters, right? And once again, we asked for the distance, the total traveled distance, right? For the displacement, that's different. For the displacement, we're gonna use the signs exactly like it says. So the white area, that is 50, and the green area is negative 25. So the total displacement of the object would be 25 meters. That is kind of like telling me the object starts here at a 0 position, travels 50 meters in the positive direction, and then back 25 meters in the negative direction to end up at a final position of 25 meters from this original position over here. So everything we've been talking about in this one-dimensional motion, it's translated to graphs. And so one more quick example to show you guys how these things match up together. What we do is we draw our position versus time graphs, and the velocity versus time graphs that we're going to use tell the same story that we're talking about. So for example, I'm going to have my initial x position start some distance away from it. I'm going to have some kind of negative velocity. I'm going to sit at that 0 position for a little bit. And then I'm going to accelerate away from the object. Now what happens here is the velocity versus time graph has to match that same question, so the color coding should make sense. There's that chunk right there. I have a negative velocity occurring, so I'm going to jump down here to have negative velocity for a little bit. The object is sitting at rest at 0, so once again, the object is sitting at rest. And then the object accelerates for a period of time. And so the color coding should tell me what's going on here. So let's label position versus time graph. So right now, the object here is at rest, some position away. Here, the object is at rest. Remember, for velocity versus time graph, it's not telling us where it is. It's just telling us if it's has a positive velocity or negative velocity at the time. Here, we have a negative velocity. Here, what we have here, this is a negative velocity, and it is constant. It's a straight line. I should probably put constant up here. The green part is once again at rest. And then the yellow part is where the object is accelerating in the positive direction, speeding up in the positive direction. And that is a quick nutshell in how this graphical analysis idea works. We can take a look at the area of the velocity versus time graph, and the areas we'd be looking at would be this guy down here, and kind of figuring out where this guy should go here, this guy right here. So we would have this area that would be positive, and this area that would be negative. So for total displacement, We would add them up and make sure we take the signs into account, the positive thing minus the negative thing. For the total distance, I would add them both up to get how far the object actually traveled. Once again, throw some numbers in there. We're using some examples we have, and that's how you would figure that out. All right, thanks for watching. If you have any questions, let me know. Bye.